All right. Hello, everyone. So glad to see everyone here. I am hoping that you guys are having a great summit so far and very excited with all the new things that you must be hearing from different sessions and, of course, in the keynote. I am Neetu Nivedita. I am a managing director within Accenture. I lead our data and AI solutions, especially around generative AI solutions for industries. So I lead many of our new developments that we are doing as part of our industry solutions using large language models, fine-tuning the models on Databricks, AWS, and everything. So today, I'm going to talk about three industry solutions, or rather three use cases. And what I do want to say is you may have heard, as you may have heard in the keynote and whatnot, all the new things that's coming, whether it's Mosaic AI, whether it's the data intelligence platform or the DBRX, the importance of open source LLMs and whatnot. That's great, but my intention in this session is to equip you to know how practically all of this comes together. So we have all of these, great, but how do you build an actual application that will be practical, that can be used, and from which you can derive value? So with that, I welcome you all to this session. I'll go over the slides and some demos, but at the end of it, please feel free to ask me questions, and I'll be happy to answer and make this interactive. So with that, let me move on. So in today's agenda, we will go through three use cases. The first two, which is DBRX and the Mosaic AI, will cover most of our content. The final one will be around Llama 2 and how we are using Mosaic AI for the whole production-grade solution for Llama 2. So that's a bonus use case. I'll talk about that at the end. But the main focus is going to be on two different use cases, completely in two separate industries, to show you the power of GenAI and LLMs that can be applied across multiple industries. So before I begin, I do want to say thank you to the AV team for setting all this up. Thank you to all of you for coming. And thanks to Jeffrey, who's not hearing this. By the way, he told me to give him a shout out. So thank you to him. And I hope you enjoy this session. So moving on, this is the main sort of the context. So let me set the context a little bit. Now, you may have heard that there are several architectural patterns for creating GenAI applications. This is different from the traditional engineering solutions we have been doing for the past decade, and I come from an engineering background, by the way. So I've been doing a lot of Java, regular stuff, web services and whatnot. But now the architectural patterns for creating GenAI applications can be divided into four main categories. So the first one is prompt engineering, and then we have RAG, which is retrieval augmented generation. You have fine-tuning, and you have pre-trained from scratch. So the thing here is that for the second and the third one that you see on the screen, RAG and fine-tuning, our solutions and architectures that we will see today, the solutions, they will involve these two architectural patterns. And pre-trained from scratch, of course, is the most complex. So if you see, the complexity increases as you go from prompt engineering to pre-train. So we will talk about RAG and fine-tuning and how we have done this and sort of scaled this in production. Again, these are extremely new, using DBRX and everything. So, it's still evolving, so to speak, to be honest. It is still going through iterations, so it is by no means complete. But let me introduce the use cases for the two. So if you see for the RAG, what we are doing is we are employing, or rather creating, an intelligent auto insurance AI assistant, and I'll show you a demo of that, using the RAG approach. So this is a conversational AI agent. It's a multimodal thing. It can take images and talk to you like a regular person. So why is this important? This is not your regular chatbot. So those days are gone. Now we are employing a really intelligent, smart AI assistant that can understand your intent. So I don't know if you guys have heard Jensen Huang talking about this repeatedly, even on the earnings call for NVIDIA. We are moving away from instruction-based, computers to understanding of intent kind of computers. So this is where the AI assistant is intelligent. It understands, it tries to understand your intent versus just following some dumb rules, okay? The second use case is around fine-tuned LLM. So that's not RAG. So the first one is RAG. The second one is fine-tuned LLM, which is for, so what we did here is for a healthcare company and for a manufacturing company, we were trying to create a solution that would help their CEO, CXO, CHRO to create a full talent strategy platform. So, in an organization, there are several, people, employees and all that. The CXOs have this really big, important responsibility of making sure the talent strategy is really good. So how we are using LLM to solve that problem, that's going to be our second use case. So moving on to the next, why DBRX and Mosaic? So for the first use case, which is using insurance, which I will show about the insurance AI assistant, it is powered by DBRX. It uses DBRX behind the scenes. And for the second one, it's entirely on Mosaic AI. And you may have heard in the keynote also the data intelligence platform that Databricks has now, it's all Mosaic AI. So you have training, serving, ML flow, governance, everything end-to-end designed for LLMs there. So that's the Mosaic AI one, which we will see as part of the second example. DBRX, of course, is one of the best performing open source models now, designed by and created by Databricks. They were able to measure it against Gemini. They were able to measure it against GPT 3.5, and it actually surpasses performance there. Why? What is so great about it? The secret ingredient is around the architecture of MOE, mixture of experts, which DBRX employs, and I'll talk about that in a second of why that is so important. It was trained on, as you can see, more than 3,000 NVIDIA Hopper chips. It uses the open source libraries, Foundry, Streaming, Mega Blocks, which also, by the way, was recently released to the public. And then the main key point for DBRX is it's cheaper and faster. So faster in inference and really much less compute intensive, much less cost to train it. That's the LLM. Now let's talk about Mosaic AI. That's the whole end-to-end platform for building, owning, governing all of these LLMs, right? It's not, so the thing here is that as you may have done earlier in all our other engineering solutions, we were kind of doing it in a way where the gamut of our, whether it's tuning or engineering was only so much. With LLMs, there are new complexities, and we need a new kind of end-to-end platform for governance and everything. And that's where Mosaic AI makes our lives as AI developers really easy. So let me pause here for a second. Have you guys worked with DBRX? How many of you have worked with DBRX, if at all? Then I can gear my, okay, only a few, okay. So I'll try to incorporate, in very clear terms, why and how it's important, what lessons we have learned by burning our fingers and hands while doing this, so that you can save more time going forward. But we'll talk about that. So let's start with DBRX. So this was our main challenge. Now, many of you may have had some experience with insurance, right? Auto insurance, be it health insurance, whatever. This is auto insurance. If by chance, God forbid, there is a minor or major collision, there have been mostly times where you go, kind of in circles with the insurance agents, with the call center people. You don't really get an answer. it's very frustrating many times because you're just circling and circling. You don't know how much of your coverage is there, deductible, what is the resolution for the claim estimation, and all of that. Plus, there is no person that's available 24/7. So what we did was, the other thing, before I talk about the solution, the other thing is thousands and thousands of pages of manual. Oh my God, the policy documents that you have to go through to understand the manual, it's exhausting. So this was a perfect use case where machine, as an LLM, can really help do all of that stuff and give us answers that we need. So we created a full end-to-end solution with the DBRX endpoint, with the DBRX LLM model. And what we did was we used LangChain extensively. We created this whole thing with two front ends. One which would help as an AI assistant to answer our questions, and the other that would help us or help the user submit a claim, or even put in an image of your car and tell you what would be your coverage, what is the insurance amount that you might be able to secure. So really helpful, 24/7 available. You don't have to go through all the policy documents. You don't have to talk to an agent for 10 times, calling them back, waiting for their call, spending hours. You literally get the answers you need. And that's important. The answers you need, personalized to you, very quickly, along with policy recommendations. So thereby, you have saved hundreds of hours of yourself as customer, and the company has saved a lot of money that they would have paid otherwise, lingering this for a longer time. So this is the value proposition. So let's, I talked about this a little bit, but I want to really discuss why it's important. And while I talk about this in this slide and next, it's not just for insurance, mind you. It could be applicable to other industries as well, because this is all about two things: cost savings, time saving. And we all know we don't want to sit on the calls forever trying to get some answer. We want to move on, maybe watch Netflix, whatever. But so these are the things which would help really the customer from the experience standpoint, as well as the organization from cost standpoint. So insurance industry traditionally had the blue bars where you submit a claim, there is manual data processing, there'll be like 100 questions, you'll be answering the same thing over and over again. There could be errors because there's human judgment involved, and there could be other policies that the call agent or the agent handling this has not seen, and all of that. It takes about 3 to 4 weeks. On an average, if it's really fast, maybe 2 to 3 weeks. From that, we were able to reduce it to just a couple of days or 3 days because we were employing all of these streamlined processes. So that's the use case and the solution. But let's look at the engineering that's going on behind the scenes, because that's more important. We want to look at what the architecture is. Does it scale? How do I put it in production? And how do I make sure that it's not a one-time thing? Right? Because policy documents will change. There will be new documents, there'll be new things. So how does all of this work? So model, retrieval, and UI orchestration. There are 3 components to this whole solution. As I mentioned, that this is a RAG-based solution. So we have this whole retrieval at the middle, which is really important. DBRX Instruct is the model we are using. And I mentioned at the upfront, start of the slide that it has an MOE, mixture of experts, design built within it. So traditionally, the LLMs, they used to have dense feed-forward networks, neural networks, in which case all the neurons were being used for providing an answer and inference. The problem with that is whether it's training or inference, it takes a lot of time because it's a dense model. The MOE models are sparse, meaning it is a collection of experts. Each expert is a neural network, and there is a gating mechanism that actually sends certain tasks to each expert, meaning each expert is specializing only in a certain task. So when there is a problem or a question, it is divided up. the gating or mechanism or the routing router or the component that is actually manning the whole gating mechanism tries to select the expert it would send that task to. So not all of them are used. So why is this important? Number one, it is extremely fast to train. It is computationally much less intensive, means the cost is much less. As a result of which, the use of DBRX, and in fact, DBRX itself was, I think, pre-trained in a matter of months, we were able to use it as well for specific use cases where it was given to us at a cheaper rate. So that's the whole point of MOE. It is not like the other LLM, so that's what it is built on. The other thing is it has 32,000 tokens. I'll talk about that and why that is important. We used a paper token serving model. I'll show you that in a second. The most important thing on this slide, if at all, you have to take one key takeaway, it's the retrieval. It's the vector database. And I'll explain why that's important. But that is the heart. According to me personally, if you were to ask me, that is the heart. I mean, yes, the LLM is great and everything, but the vector database is super, super important. We are using an embedding model provided by Databricks, really efficient, really nice, and I will also explain about that. Finally, UI and orchestration is through LangChain and Streamlit. LangChain, you guys, many of you must be using LangChain, I think, but LangChain, I think from October 2022, was the fastest growing open source project. It was really famous. It was widely used. It is awesome in orchestration, especially of all these GenAI applications. So we are using that. Streamlit, of course, for our user interface. And with Streamlit, we collect user feedback. You remember the little thumbs up, buttons and all that in ChatGPT. So we did that also in our app. So Streamlit helps us do that. So this is the full end-to-end thing of what model, what LLM we are using, how the RAG, what kind of vector database and orchestration. But let's move on to the nitty-gritty of it. Okay, this is the full end-to-end process flow. This is literally, how we have set it up, and it's been working. We are now advancing this, making this more intense in the sense that it should be able to handle more use cases. So what is this? Let me start from the first, the thing at the left, okay? I'm gonna see if my laser works. Or maybe not. Do you guys see a laser? I don't even see it.
Sometimes you do.
Is it there? I can't even see where it is. Okay. Okay, it's too small. Like, I can't see. It's fine. I'm going to talk. So the first one, data preparation and indexing. So we ingested hundreds of manuals to understand the policies, FAQs of the auto insurance company, incident index. There is claims, the claims policies and manuals. There was a whole lot of thousands of documents, okay? A lot of documents. Those documents will provide the context to the AI assistant to answer. So it was essential to ingest that. Now, the way GenAI or LLM applications work is the assistant cannot obviously understand English. The computer program can't understand that. We have to convert it into embeddings, okay? And embedding is nothing but just a vast array of floating point numbers. And so every document was divided, sliced, and diced to create manageable chunks, because you cannot send the whole document for embedding. That's not going to work. So we divided each of the documents, into chunk sizes. We sent the chunks to the embedding model, which in this case, over here, you see Databricks BGE large N. That's the one we used. It is a managed process. So there are two ways you can send, you can create embeddings. Either managed, which is the top, everything that you see at the top, that's the managed one. That's only for text. We also had another portion, if you remember, if you saw in the demo, of the assistant that was taking images. For that embedding is not going to work. So the bottom half of the diagram that you see, TensorFlow SqueezeNet is what we used for the image embeddings. So that's for the image. The top one is for text. All of that is, first it is cleansed, then we slice and dice it into chunks, and we send it for get to the endpoints for getting the embeddings. Once we get the embeddings, that's where the Databricks vector search index comes into play. It is something that Databricks has. It creates an index on top of the Delta Lake table where your chunks are stored, the embeddings are stored. It creates an index. Why? So it goes back to our regular database theories, age-old. When you're doing a search and when you're trying to augment information from your database with the answer the assistant is providing, you need a really fast retrieval. How do you get a fast retrieval if you want to do this? You get it through the index. So the vector search index makes it easy during inferencing for the documents, the matching documents, to be sent to the AI assistant. So that's what the vector search index is. So everything that you see till 3, that is number 1 and 2, are like stage 1. You need to do that before doing anything else. That's literally setup. That's like the stage setup. Okay, so that's the stage setup. So we did that. Hundreds and thousands of manuals were cleansed. We got them, cleansed them, divided them, created the embeddings, and stored them. One thing to add here before I move on to number 3 is, for the text, I mentioned that Databricks has this managed way, which is the upper one you see, managed vector indexing. But for TensorFlow, SqueezeNet, or for that matter, if you use anything else to create embeddings, but not the Databricks endpoint or model, it's your responsibility to make sure those embeddings are inserted in the Delta Lake table. So that is something to note. It's like a tip. You'll have to figure it out how to insert in Delta Lake table. Otherwise, for the first half, Databricks takes care of everything. So we are done with 1 and 2. Number 3. Now let's see this. Now let's look at 4 before we go to 3. So you're a user. You're typing in your question, which is the first, at the top, which is regular question answer. What happens is your question is converted into embeddings. Now here's the second pro tip. The model you use, the LLM that you use for creating the embeddings of the documents has to be the exact same model you will use for creating the embeddings of the question. So it's not like your question embedding is something and this is something. That's not going to work. So you have to make sure that both models are the same. So for the first one, obviously we used BGE, converted the question into embeddings. That embedding was then, we did a similarity search. There is a way in Databricks to trigger the similarity search. It goes and checks in the vector index, the top 3, 4, whatever, matches with that question. It retrieves that and sends to the DBRX endpoint for a combined answer. The third and final pro tip here, is this. So the assistant's intelligence is measured by how much context it has. If it has context, great, it'll give you a great answer. It doesn't have context, it won't. The context, AKA what it gets from the index, is what makes it intelligent, okay? That's like literally bare bones. So the limitation here is that the window size of the LLM, which in this case, DBRX has a window size of 32,000 tokens. The window size is what determines how much of context you can put in. Meaning, the prompt plus answer cannot exceed the window size of the LLM, in this case, 32K. So it's important that you divide the initial documents in stages 1 and 2 into certain chunks so that your entire context that comes from the search and your instruction within the prompt that goes to the endpoint, along with the answer that comes out of the endpoint, everything is within the 32,000 window size. So that's really important. Okay, so we did that, and then we have the bottom half on the right side for number 3 and 4 is for the exact same thing, but images. So we have two, a text assistant and an image assistant. and both follow similar process, but slightly different because of the process of creation of embeddings and search of embeddings. So in the interest of time, I know I have 10 minutes, so I'll move on. That was the process flow. This is the deployment picture. So we used, as you can see, there are the 4 boxes with the dotted lines. Those are all Databricks, deployment, most important Databricks components that are being used for the production deployment. So you have at the top, try my laser again. Okay, yeah, there it is. So this one, LLM pipeline, this one right over here, the first one is for your creation. You have your vector database embedding, which I just talked about. You have your LLM pipeline deployment and monitoring workflow. I want to call out 2 things here. Number 1, lakehouse monitoring, which you cannot see because of the caption thingy here, but lakehouse is right here at the bottom. The lakehouse monitoring is super important for the monitoring workflow. This is where it's actually determining if something goes wrong. If your assistant is giving all kinds of answers, this is where the detection happens. And we have proactive reporting, by the way, from lakehouse for that. And then you have the ML flow here, which nicely integrates with, we are using, of course, LangChain and DBRX here, but you can see ML flow nicely integrates with all of that for making sure that your whole deployment is pretty smooth. This is the picture for the end-to-end sort of deployment, which also includes the experimentation point at the top, if you see. But the previous one was the whole process pipeline of how do you set up all the components. So moving on to my next use case, and I'm going to keep it a little faster here because I want to leave some time for questions too, and I have just 10 minutes to go. So Mosaic AI, and like I said, is the full end-to-end thing, and you may have heard it's really pretty cool. So this use case, we are now moving away from insurance to talent strategy. How do you help companies create a talent strategy? Again, this is the problem statement, but it can be really used for any other problem statement. The behind-the-scenes engineering still more or less remains the same. The problem statement differs. In this case, we were trying to create a classifier for understanding, let's say there are 100,000 employees in an organization. How do we classify and show and kind of come up with a map of where everyone is so that we can create personalized upskilling pathways for everyone? This is different from RAG. RAG is not going to help here. Now, how do you decide when to do RAG, when to do fine-tuning? In the previous use case where the assistant could just answer with documentation that was given to it, that's a great use case for RAG. This is a much, much more intensive question and use case, so RAG won't help. This is more like a place where the LLM itself has to be intelligent enough with the organization's data, and that's where we need to fine-tune this. Let me play this video to set the context of what this is, why the classification of different roles and skills are important, more important in this case. And while you watch this, keep in mind 3 things. In the previous case, the model was DBRX. The platform we used, of course, was with Databricks and everything, and LangChain. And we used the RAG mechanism. Here, the model is MPT, which is the Mosaic Foundation models, as you may have heard. We're still using LangChain, but we are using fine-tuning instead of RAG. So I'm going to play this.
Identifying and classifying skills and roles is more crucial than ever. Join us as we explore the skills.ai role and skill classifier, powered by Mosaic AI, and discover how this innovative solution is transforming talent management. Let's dive into this solution's key features and outcomes. This model is fine-tuned on 3 binary classifications for roles and skills, helping users identify cloud, digital, and data-driven roles and skills. By considering the classification context, role name or skill name, and description, the model accurately aligns descriptions with specific values. Our model doesn't just provide a classification, it also offers detailed reasoning behind decisions. The model identifies key points from the context and explains why a description does or does not align. This level of detail leads to more accurate predictions and defensible results. Finally, we offer client custom goal classification. Thanks to the focus on classification context and descriptions, clients can create their own goals without needing to train a new model. This customizable goal framework allows clients to better align with their strategic objectives while significantly accelerating value from weeks to days. These powerful features make for an indispensable tool in modern talent management, driving precision, transparency, and customization. Training the skills.ai role and skill classifier involves three essential elements. The model. At its core lies GPT-7b, a language model trained on 1 trillion tokens of English text and code. Its architecture was built for efficiency and prepared to handle long inputs. Training. Powered by Mosaic AI, our process emphasizes speed, accuracy, and cost efficiency. Mosaic AI Composer seamlessly integrates with popular ML frameworks, while the LLM Foundry offers an open-source toolkit for streamlined training and deployment. Training data generation, guided by human feedback, DSPY refines prompts passed to GPT 3.5 Turbo for generating synthetic data. Human validation and enhancement ensure accuracy throughout the training process. Together, these elements contribute to an innovative, efficient, and accurate approach to role and skill classification. Embrace the future of talent management with our advanced AI model, spearheading industry progress with cutting-edge technology and unmatched precision.
Okay, so this was with MPT, like I mentioned.
In today's rapidly evolving...
Let's look at the architecture, and then we can quickly go through the whole end-to-end architecture like we did for the last time. The same process here, the model is MPT-7b, really good model, by the way. And as you can see, it was we used it, we found value with it. For the training and everything, we used also the for the fine-tuning and making it a little bit better and more domain-centric. We were really using the Composer library as well as streaming, and that's all part of the Mosaic ML research that they have done. For data generation, now here's the tricky part here. Prompt engineering until now, you must have done manually. It takes a while to get to the right level of answers we want to. DSPY makes it really easy for AI developers to kind of automate the process of prompt engineering. So what it does is iteratively, it's going to, if you tell DSPY what exactly is the response or the output you're looking for, it's able to programmatically iterate and reduce your manual effort in prompt engineering. So it's a pretty cool framework. You can check it out when you get a chance. It kind of optimizes LLM prompts as well. And there is this whole programmatic support to avoid more manual effort. Internally, of course, the model used by DSPY is GPT 3.5 Turbo, and we used actual data, the client data, our own data, plus synthetic data as well for fine-tuning because it was a more involved process. So moving on, this is the whole end-to-end architecture with the Mosaic AI platform and how we have done this. I want to call out 4 main things here. Number 1 is the training. Super important. As you can see here, we're using the Composer and streaming libraries to make sure that we can do the distributed training as well as fine-tune more with the domain data. The model serving, which is, where is it? Number 2 right there. It has live inference right over here, live inference, batch inference, and streaming inference as well. Number 3, which is the model registry and more around how do we use MLflow. So we are using MLflow a lot for governance here. This was a tricky part for us because it was a fine-tuned model. A lot of client data was being used. Privacy was of utmost concern. And so governance obviously took an unprecedented level of our attention. And so MLflow really helped us there. And then of course we have the lakehouse monitoring just like we had earlier. So that's about it. And thank you. Thank you so much.